is another moth, the Sweateria form of Biston cognitaria, first noticed in industrialized areas such as Chicago and New York City in the early 1900s. By 1961 it constituted over 90% of the population in parts of Michigan. The idea that natural selection was responsible for the changing ratio of dark to light-colored peppered moths was developed in the 1950s by H. B. D. Kettlewell of Oxford University. If natural selection was the explanation, then there should be different survival rates for dark and light-colored moths. To determine whether this was true, Kettlewell released thousands of light and dark moths into rural and industrialized areas. In the non-industrial area of Dorset, he recaptured 14.6% of the pale forms but only 4.7% of the dark forms. In the industrial area of Birmingham, the situation was reversed, 13% of pale forms but 27.5% of dark forms were recaptured. Clearly some environmental factor was responsible for the greater survival rates of dark moths. Birds were predators of peppered moths. Kettlewell hypothesized that the normal pale forms are difficult to see when resting on lichen-covered trees, whereas dark forms are conspicuous. In industrialized areas, lichens are destroyed by pollution, tree barks become darker, and dark moths are the ones birds have difficulty detecting. As a test, Kettlewell set up hidden observation positions and watched birds voraciously eat moths placed on tree trunks of a contrasting color. The action of natural selection in producing a small but highly significant step of evolution was seemingly demonstrated, with birds as the selecting force. Not every researcher has been convinced that natural selection by birds is the only explanation of the observed frequencies of dark and light-peppered moths. More recent data, however, provide additional support for Kettlewell's ideas about natural selection. The light-colored form of the peppered moth is making a strong comeback. In Britain, a Clean Air Act was passed in 1965. Sir Cyril Clarke has been trapping moths at his home in Liverpool, Merseyside, since 1959. Before about 1975-90% of the moths were dark, but since then there has been a steep decline in melanic forms, and in 1989 only 29.6% of the moths caught were melanic. The mean concentration of sulfur dioxide pollution fell from about 300 micrograms per cubic meter in 1970 to less than 50 micrograms per cubic meter in 1975 and has remained fairly constant since then. If the spread of the light-colored form of the moth continues at the same speed as the melanic form spread in the last century, soon the melanic form will again be only an occasional resident of the Liverpool area. TPO 37. TPO 37 Passage 1. Thales and the Milesians. While many other observers and thinkers had laid the groundwork for science, Thales, the best known of the earliest Greek philosophers, made the first steps toward a new, more objective approach to finding out about the world. He posed a very basic question: what is the world made of? Many others had asked the same question before him, but Thales based his answer strictly on what he had observed and what he could reason out, not on imaginative stories about the gods or the supernatural. He proposed water as the single substance from which everything in the world was made and developed a model of the universe with Earth as a flat disk floating in water. Like most of the great Greek philosophers, Thales had an influence on others around him. His two best-known followers, though there were undoubtedly others who attained less renown, were Anaximander and Anaximenes. Both were also from Miletus and so, like Thales, were members of the Milesian school. Much more is known about Anaximander than about Anaximenes, probably because Anaximander, who was born sometime around 610 BC, ambitiously attempted to write a comprehensive history of the universe. As would later happen between another teacher-student pair of philosophers, Plato and Aristotle, Anaximander disagreed with his teacher despite his respect for him. He doubted that the world and all its contents could be made of water and proposed instead a formless and unobservable substance he called a pyrrhon that was the source of all matter. Anaximander's most important contributions, though, were in other areas. Although he did not accept that water was the prime element, he did believe that all life originated in the sea, and he was thus one of the first to conceive of this important idea. Anaximander is credited with drawing up the first world map of the Greeks and also with recognizing that Earth's surface was curved. He believed, though, that the shape of Earth was that of a cylinder rather than the sphere that later Greek philosophers would conjecture. Anaximander, observing the motions of the heavens around the pole star, was probably the first of the Greek philosophers to picture the sky as sphere completely surrounding Earth, an idea that, elaborated upon later, would prevail until the advent of the scientific revolution in the 17th century. Unfortunately, most of Anaximander's written history of the universe was lost, and only a few fragments survive today. Little is known about his other ideas. Unfortunately, too, most of the written work for Anaximenes, who may have been Anaximander's pupil, has also been lost. All we can say for certain about Anaximenes, who was probably born around 560 BCE, is that following in the tradition of Anaximander, he also disagreed with his mentor. The world, according to Anaximenes, was not composed of either water or a pyrron, but air itself was the fundamental element of the universe. Compressed, it became water and earth, and when rarefied or thinned out, it heated up to become fire. Anaximenes may have also been the first to study rainbows and speculate upon their natural rather than supernatural cause. With the door opened by Thales and the other early philosophers of Miletus, Greek thinkers began to speculate about the nature of the universe. This exciting burst of intellectual activity was for the most part purely creative. The Greeks, from Thales to Plato and Aristotle, were philosophers and not scientists in today's sense. It is possible for anyone to create ideas about the nature and structure of the universe, for instance, and many times these ideas can be so consistent and elaborately structured, or just so apparently obvious, that they can be persuasive to many people. A scientific theory about the universe, however, demands much more than the various observations and analogies that were woven together to form systems of reasoning, carefully constructed as they were, that would eventually culminate in Aristotle's model of the world and the universe. Without experimentation and objective, critical testing of their theories, the best these thinkers could hope to achieve was some internally consistent speculation that covered all the bases and satisfied the demands of reason. TPO 37 Passage 2. Direct species translocation. It is becoming increasingly common for conservationists to move individual animals or entire species from one site to another. This may be either to establish a new population where a population of conspecifics has become extinct or to add individuals to an existing population. The former is termed reintroduction and the latter reinforcement. In both cases, wild individuals are captured in one location and translocated directly to another. Direct translocation has been used a wide range of plants and animals and was carried out to maintain populations as a source of food long before conservation was a familiar term. The number of translocations carried out under the banner of conservation has increased rapidly, and this has led to criticism of the technique because of the lack of evaluation of its efficacy and because of its potential disadvantages. The nature of translocation ranges from highly organized and researched national or international programs to ad hoc releases of rescued animals by well-intentioned animal lovers. In a fragmented landscape where many populations and habitats are isolated from others, translocations can play an effective role in conservation strategies. They can increase the number of existing populations or increase the size, genetic diversity, and demographic balance of a small population, consequently increasing its chances of survival. Translocation clearly has a role in the recovery of species that have substantially declined and is the most likely method by which many sedentary species can recover all or part of their former range. However, against this is the potential for reinforcement translocations to spread disease from one population to another or to introduce deleterious or maladaptive genes to a population. Additionally, translocation of predators or competitors may have negative impacts on other species, resulting in an overall loss of diversity. Last but not least of these considerations is the effort and resources required in this type of action, which need to be justified by evidence of the likely benefits. Despite the large number of translocations that have taken place, there is surprisingly little evidence of the efficacy of such actions. This is partly because many translocations have not been strictly for conservation, neither have they been official nor legal, let alone scientific in their approach. Successful translocations inevitably get recorded and gain attention, whereas failures may never be recorded at all. This makes appraisal of the method very difficult. One key problem is a definition of success. Is translocation successful if the individuals survive the first week or a year, or do they need to reproduce for one or several generations? Whatever the answer, it is clear that a general framework is required to ensure that any translocation is justified, has a realistic chance of success, and will be properly monitored and evaluated for the benefit of future efforts. An example of apparent translocation success involves the threatened Seychelles warbler. This species was once confined to Cousin Island, one of the Seychelles Islands, and reduced to 26 individuals. Careful habitat management increased this number to over 300 birds, but the single population remained vulnerable to local catastrophic events. The decision was taken to translocate individuals to 2 nearby islands to reduce this risk. The translocations took place in 1988 and 1990, and both have resulted in healthy breeding populations. A successful translocation exercise also appears to have been achieved with red howler monkeys in French Guiana. A howler population was translocated from a site due to be flooded for hydroelectric power generation. The release site was an area where local hunting had reduced the density of the resident howler. Population released troopsoff monkeys were kept under visual observation and followed by radio tracking of 16 females. Although the troops appeared to undergo initial problems, causing them to split up, all the tracked females settled into normal behavioral patterns. Unfortunately, the success stories are at least matched by accounts of failure. Reviewing translocation of amphibians and reptiles, researchers C. Kenneth Dodd and Richard A. Siegel concluded that most projects have not demonstrated success as conservation techniques and should not be advocated as though they were acceptable management and mitigation practices. TPO 37 Passage 3. Modern architecture in the United States. At the end of the 19th century, there were basically 2 kinds of buildings in the United States. On one hand were the buildings produced for the wealthy or for civic purposes, which tended to echo the architecture of the past and to use traditional styles of ornamentation. On the other hand were purely utilitarian structures, such as factories and grain elevators, which employed modern materials such as steel girders and plate glass in an undisguised and unadorned manner. Such buildings, however, were viewed in a category separate from fine architecture, and in fact were often designed by engineers and builders rather than architects. The development of modern architecture might in large part be seen as an adaptation of this sort of functional building and its pervasive application for daily use. Indeed, in this influential book Toward a New Architecture, the Swiss architect Le Corbusier illustrated his text with photographs of American factories and grain storage silos, as well as ships, airplanes, and other industrial objects. Nonetheless, modern architects did not simply employ these new materials in a strictly practical fashion, they consciously exploited their aesthetic possibilities. For example, glass could be used to open up walls and eliminate their stone and brick masonry because large spaces could now be spanned with steel beams. The fundamental premise of modern architecture was that the appearance of the building should exhibit the nature of its materials and forms of physical support. This often led to effects that looked odd from a traditional standpoint, but that became hallmarks of modern architecture for precisely this reason. For example, in traditional architecture, stone or brick walls served a structural role, but in a steel beam building the walls were essentially hung from the internal skeleton of steel beams, which meant that walls and corners no longer needed to be solid but could be opened up in unexpected ways. At the Fages shoe factory in Germany, for example, German architect Walter Gropius placed glass walls in the corners, effectively breaking open the box of traditional architecture and creating a new sense of light and openness. Similarly, steel beams could be used to construct balconies that projected out from the building without any support beneath them. These dramatic balconies quickly became a signature of modern architects such as Frank Lloyd Wright. Wright's most dramatic residence, Falling Water, has balconies that thrust far out over a stream in a way that seems to defy gravity. The ways in which new technology transformed architectural design are dramatically illustrated through the evolution of the high-rise office building. After 10 or 12 stories, masonry construction reaches a maximum possible height, since it runs into difficulties of compression and of inadequate lateral strength to combat wind shear. Steel construction, on the other hand, can support a building of 50 or 100 stories without difficulty. Such buildings were so different from any previous form of architecture that they quickly acquired a new name, the skyscraper. From the standpoint of real estate developers, the purpose of skyscrapers was to increase rental space in valuable urban locations. But to create usable high-rise buildings, a number of technical challenges needed to be solved. One problem was getting people to the upper floors, since after 5 or 6 stories it becomes exhausting to climb stairs. Updated and electrified versions of the freight elevator that had been introduced by Elisha Graves Otis in 1853 solved this problem. Another issue was fire safety. The metal supporting buildings became soft when exposed to fire and collapsed relatively quickly. However, when the metal is encased in fire-retardant materials, its vulnerability to fire is much decreased. In Chicago, a system was developed for surrounding the metal components with hollow tiles made from brick-like terracotta. Such tiles are impervious to fire. The terracotta tiles were used both to encase the supporting members and as flooring. A structure built with steel beams protected by terracotta tiles was still 3 times lighter than a comparably sized building that used masonry construction, so the weight of the tiles was not a problem. TPO 38. TPO 38 Passage 1. Microscopes. Before microscopes were first used in the 17th century, no one knew that living organisms were composed of cells. The first microscopes were light microscopes, which work by passing visible light through a specimen. Glass lenses in the microscope bend the light to magnify the image of the specimen and project the image into the viewer's eye or onto photographic film. Light microscopes can magnify objects up to 1,000 times without causing blurriness. Magnification, the increase in the apparent size of an object, is one important factor in microscopy. Also important is resolving power, a measure of the clarity of an image. Resolving power is the ability of an optical instrument to show 2 objects as separate. For example, what looks to the unaided eye like a single star in the sky may be resolved as 2 stars with the help of a telescope. Any optical device is limited by its resolving power. The light microscope cannot resolve detail finer than 0.2 micrometers, about the size of the smallest bacterium. Consequently, no matter how many times its image of such a bacterium is magnified, the light microscope cannot show the details of the cell's internal structure. From the year 1665, when English microscopist Robert Hooke discovered cells, until the middle of the 20th century, biologists had only light microscopes for viewing cells. But they discovered a great deal, including the cells composing animal and plant tissues, microscopic organisms, and some of the structures within cells. By the mid-1800s, these discoveries led to the cell theory, which states that all living things are composed of cells, and that all cells come from other cells. Our knowledge of cell structure took a giant leap forward as biologists began using the electron microscope in the 1950s. Instead of light, the electron microscope uses a beam of electrons and has a much higher resolving power than the light microscope. In fact, the most powerful modern electron microscopes can distinguish objects as small as 0.2 nanometers, a 1,000-fold improvement over the light microscope. The period at the end of this sentence is about 1,000,000 times bigger than an object 0.2 nanometers in diameter, which is the size of a large atom. Only under special conditions can electron microscopes detect individual atoms. However, cells, cellular organelles, and even molecules like DNA and protein are much larger than single atoms. Biologists use the scanning electron microscope to study the detailed architecture of cell surfaces. It uses an electron beam to scan the surface of a cell or group of cells that have been coated with metal. The metal stops the beam from going through the cells. When the metal is hit by the beam, it emits electrons. The electrons are focused to form an image of the outside of the cells. The scanning electron microscope produces images that look three-dimensional. The transmission electron microscope, on the other hand, is used to study the details of internal cell structure. Specimens are cut into extremely thin sections, and the transmission electron microscope aims an electron beam through a section, just as a light microscope aims a beam of light through a specimen. However, instead of lenses made of glass, the transmission electron microscope uses electromagnets as lenses, as do all electron microscopes. The electromagnets bend the electron beam to magnify and focus an image onto a viewing screen or photographic film. Electron microscopes have truly revolutionized the study of cells and cell organelles. Nonetheless, they have not replaced the light microscope. 1. Problem with electron microscopes is that they cannot be used to study living specimens because the specimen must be held in a vacuum chamber, that is, all the air and liquid must be removed. For a biologist studying a living process, such as the whirling movement of a bacterium, a light microscope equipped with a video camera might be better than either a scanning electron microscope or a transmission electron microscope. Thus, the light microscope remains a useful tool, especially for studying living cells. The size of a cell often determines the type of microscope a biologist uses to study it. TPO 38 Passage 2. The raccoon's success. Raccoons have a vast transcontinental distribution, occurring throughout most of North America and Central America. They are found from southern Canada all the way to Panama, as well as on islands near coastal areas. They occur in each of the 49 states of the continental United States. Although raccoons are native only to the Western Hemisphere, they have been successfully transplanted to other parts of the globe. Following a decline to a relatively low population level in the 1930s, raccoons began to prosper following their 1943 breeding season. A rapid population surge continued throughout the 1940s, and high numbers have been sustained ever since. By the late 1980s, the number of raccoons in North America was estimated to be at least 15 to 20 times the number that existed during the 1930s. By now, their numbers have undoubtedly grown even more, as they have continued to expand into new habitats where they were once either rare or absent, such as sandy prairies, deserts, coastal marshes, and mountains. Their spread throughout the Rocky Mountain West is indicative of the fast pace at which they can exploit new environments. Despite significant numbers being harvested and having suffered occasional declines, typically because of disease, the raccoon has consistently maintained high population levels. Several factors explain the raccoon's dramatic increase in abundance and distribution. First, their success has been partially attributed to the growth of cities, as they often thrive in suburban and even urban settings. Furthermore, they have been deliberately introduced throughout the continent. Within the United States, they are commonly taken from one area to another, both legally and illegally, to restock hunting areas and, presumably, because people simply want them to be part of their local fauna. Their appearance and subsequent flourishing in Utah's Great Salt Lake Valley within the last 40 years appears to be from such an introduction. As an example of the ease with which transplanted individuals can succeed, raccoons from Indiana have reportedly been able to flourish on islands off the coast of Alaska. The raccoon's expansion in various areas may also be due to the spread of agriculture. Raccoons have been able to exploit crops, especially corn, but also cereal grains, which have become dependable food sources for them. The expansion of agriculture, however, does not necessarily lead to rapid increases in their abundance. Farming in Kansas and eastern Colorado proceeded rapidly in the 1870s and 1880s, but this was about 50 years before raccoons started to spread out from their major habitat, the wooded river bottomlands. They have also expanded into many areas lacking any agriculture other than grazing and into places without forests or permanent streams. Prior to European settling and farming the Great Plains region, raccoons probably were just found along its rivers and streams and in the wooded areas of its southeastern section. With the possible exception of the southern part of the province of Manitoba, their absence was notable throughout Canada. They first became more widely distributed in the southern part of Manitoba, and by the 1940s were abundant throughout its southeastern portion. In the 1950s their population swelled in Canada. The control of coyotes in the prairie region in the 1950s may have been a factor in raccoon expansion. If their numbers are sufficient, coyotes might be able to suppress raccoon populations. By the 1960s the raccoon had become a major predator of the canvasback ducks nesting in southwestern Manitoba. The extermination of the wolf from most of the contiguous United States may have been a critical factor in the raccoon's expansion and numerical increase. In the 18th century, when the wolf's range included almost all of North America, raccoons apparently were abundant only in the deciduous forests of the East, Gulf Coast, and Great Lakes regions, though they also extended into the wooded bottomlands of the Midwest's major rivers. In such areas, there are boreal habits, and the presence of hollow den trees should have offered some protection from wolves and other large predators. Even though raccoons may not have been a significant part of their diet, wolves surely would have tried to prey on those exposed in relatively treeless areas. TPO 38 Passage 3. Transgenic plants. Genes from virtually any organism, from viruses to humans, can now be inserted into plants, creating what are known as transgenic plants. Now used in agriculture, there are approximately 109 million acres of transgenic crops grown worldwide, 68% of which are in the United States. The most common transgenic crops are soybeans, corn, cotton, and canola. Most often, these plants either contain a gene making them resistant to the herbicide glyphosate, or they contain an insect-resistant gene that produces a protein called Bt toxin. On the positive side, proponents of transgenic crops argue that these crops are environmentally friendly because they allow farmers to use fewer and less noxious chemicals for crop production. For example, a 21% reduction in the use of insecticide has been reported on Bt cotton. In addition, when glyphosate is used to control weeds, other more persistent herbicides do not need to be applied. On the negative side, opponents of transgenic crops suggest that there are many questions that need to be answered before transgenic crops are grown on a large scale. One question deals with the effects that Bt plants have on non-target organisms such as beneficial insects, worms, and birds that consume the genetically engineered crop. For example, monarch caterpillars feeding on milkweed plants near Bt cornfields will eat some corn pollen that has fallen on the milkweed leaves. Laboratory studies indicate that caterpillars can die from eating Bt pollen. However, field tests indicate that Bt corn is not likely to harm monarchs. Furthermore, the application of pesticides has been demonstrated to cause widespread harm to non-target insects. Another unanswered question is whether herbicide-resistant genes will move into the populations of weeds. Crop plants are sometimes grown in areas where weedy relatives also live. If the crop plants hybridize and reproduce with weedy relatives, then this herbicide-resistant gene will be perpetuated in the offspring. In this way, the resistant gene can make its way into the weed population. If this happens, a farmer can no longer use glyphosate. 4. Example, to kill those weeds. This scenario is not likely to occur in many instances because there are no weedy relatives growing near the crop plant. However, in some cases, it may become a serious problem. For example, canola readily hybridizes with mustard weed species and could transfer its herbicide-resistant genes to those weeds. We know that evolution will occur when transgenic plants grown on a large scale over a period of time. Of special concern is the development of insect populations resistant to the Bt toxin. This pesticide has been applied to plants for decades without head development of insect-resistant populations. However, transgenic Bt plants express the toxin in all tissues throughout growing season. Therefore, all insects carrying genes that make them susceptible to the toxin will die. That leaves only the genetically resistant insects alive to perpetuate the population. When these resistant insects mate, they will produce a high proportion of offspring capable of surviving in the presence of the Bt toxin. Farmers are attempting to slow the development of insect resistance in Bt crops by, for example, planting non-transgenic border rows to provide a refuge for susceptible insects.
These insects may allow Bt susceptibility to remain in the population. Perhaps the most serious concern about the transgenic crop plants currently in use is that they encourage farmers to move farther away from sustainable agricultural farming practices, meaning ones that allow natural resources to continually regenerate over the long run. Transgenics, at least, superficially, simplify farming by reducing the choices made by the manager. Planting a glyphosate-resistant crop commits a farmer to using that herbicide for the reason, probably to the exclusion of all other herbicides and other weed control practices. Farmers who use Bt transgenics may not feel that they need to follow through with integrated pest management practices that use beneficial insects and timely applications of pesticides to control insect pests. A more sustainable approach would be to plant non-transgenic corn, monitor the fields throughout the growing season, and then apply a pesticide only if and when needed. Po 39. Po 39 Passage 1. Early writing systems. Scholars agree that writing originated somewhere in the Middle East, probably Mesopotamia, around the 4th millennium BCE. It is from the great libraries and word hoards of these ancient lands that the first texts emerged. They were written on damp clay tablets with a wedged stick. Since the Latin word for wedge is cunea, the texts are called cuneiform. The clay tablets usually were not fired. Sun drying was probably reckoned enough to preserve the text for as long as it was being used. Fortunately, however, many tablets survived because they were accidentally fired when the buildings they were stored in burned. Cuneiform writing lasted for some 3,000 years, in a vast line of succession that ran through Sumer, Akkad, Assyria, Nineveh, and Babylon, and preserved for us 15 languages in an area represented by modern-day Iraq, Syria, and western Iran. The oldest cuneiform texts recorded the transactions of tax collectors and merchants, the receipts and bills of sale of an urban society. They had to do with things like grain, goats, and real estate. Later, Babylonian scribes recorded the laws and kept other kinds of records. Knowledge conferred power. As a result, the scribes were assigned their own goddess, Nisaba, later replaced by the god Nabu of Borsippa, whose symbol is neither weapon nor dragon but something far more fearsome, the cuneiform stick. Cuneiform texts on science, astronomy, medicine, and mathematics abound, some offering astoundingly precise data. One tablet records the speed of the moon over 248 days. Another documents an early sighting of Halley's Comet, from September 22 to September 28, 164 B. C.E. more esoteric texts attempt to explain old Babylonian customs, such as the procedure for curing someone who is ill, which included rubbing tar and gypsum on the sick person's door and drawing a design at the foot of the person's bed. What is clear from the vast body of texts is that scribes took pride in their writing and knowledge. The foremost cuneiform text, the Babylonian Epic of Gilgamesh, deals with humankind's attempts to conquer time. In it, Gilgamesh, king and warrior, is crushed by the death of his best friend and so sets out on adventures that prefigure mythical heroes of ancient Greek legends such as Hercules. His goal is not just to survive his ordeals but to make sense of this life. Remarkably, versions of Gilgamesh span 1,500 years, between 2100 BCE and 600 BCE, making the story the epic of an entire civilization. The ancient Egyptians invented a different way of writing and a new substance to write on, papyrus, a precursor of paper, made from a wetland plant. The Greeks had a special name for this writing, hieroglyphic, literally sacred writing. This, they thought, was language fit for the gods, which explains why it was carved on walls of pyramids and other religious structures. Perhaps hieroglyphics are Egypt's great contribution to the history of writing. Hieroglyphic wiring, in use from 3100 BCE until 394 CE, resulted in the creation of texts that were fine art as well as communication. Egypt gave us the tradition of the scribe not just as educated person but as artist and calligrapher. Scholars have detected some 6,000 separate hieroglyphic characters in use over the history of Egyptian writing, but it appears that never more than 1,000 were in use during any one period. It still seems a lot to recall, but what was lost in efficiency was more than made up for in the beauty and richness of the texts. Writing was meant to impress the eye with the vastness of creating itself. Each symbol or glyph, the flowering reed, the owl, the quail chick, etc., was a tiny work of art. Manuscripts were compiled with an eye to the overall design. Egyptologists have noticed that the glyphs that constitute individual words were sometimes shuffled to make the text more pleasing to the eye with little regard for sound or sense. Po 39 Passage 2. The extinction of Moa. Between 80 and 85 million years ago, Gondwanaland, a giant continent made up of what today is Africa, Antarctica, Australia, and South America, broke up, thus causing what is now New Zealand to become separated from the larger landmass. After the separation, Any creature unable to cross a considerable distance of ocean could not migrate to New Zealand. Snakes and most mammals evolved after the separation. Thus there are no New Zealand snakes, and bats, which flew there, and seals, which swam there, were the only mammals on New Zealand when Polynesian settlers arrived there about 1,000 years ago. When the Maori arrived in New Zealand, they encountered birds that had been evolving for 80 million years without the presence of mammalian predators. The most striking of these animals must have been moa. Now extinct, moa were gigantic wingless birds that stood as much as 10 feet tall and weighed as much as 550 pounds. They are known from a diverse array of remains including eggshells, eggs, a few mummified carcasses, vast numbers of bones, and some older fossilized bone. The species of moa that are currently recognized occupied ecological niches customarily filled elsewhere by large mammalian browsing herbivores. They may have had relatively low reproductive rates. Apparently, they usually laid only one egg at a time. It seems possible that when Captain James Cook first visited New Zealand in 1769, moa may have still survived in the remote areas in the western part of New Zealand's South Island. If so, these individuals would have been the last of their kind. Climatic conditions in New Zealand appear to have been relatively stable over the period during which moa became extinct. Different factors could have worked in concert to account for their abrupt disappearance. Vegetation was considerably altered by the Maori occupation of New Zealand, a change not easily explained by climate variation or other possible factors. Forest and shrubland burning appears to have reduced the prime habitat of many moa species. However, the main forest burning started around 700 years ago, after what current archaeological evidence indicates was the most intensive stage of moa hunting. While there appears to have been extensive burning on the east side of New Zealand's South Island, large forest tracts remained in the most southern part of the island. Because major habitat destruction seems to have occurred after moa populations already were depleted, and because some habitat that could have sheltered moa populations remained, it would seem that other factors were also at work in the extinction of these birds. For South Island, human predation appears to have been a significant factor in the depletion of the population of moa. At one excavated Maori site, moa remains filled 6 railway cars. The density of Maori settlements and artifacts increased substantially at the time of the most intensive moa hunting. This period was followed by a time of decline in the Maori population and a societal transition to smaller, less numerous settlements. The apparent decline fits the pattern expected as a consequence of the Maori's overexploitation of moa. Finally, the Maori introduced the Polynesian rat and the dog to New Zealand. The actions of these potential nest predators could have reduced moa populations without leaving much direct evidence. The Maori may have also inadvertently brought pests and disease organisms in fowls, which could have crossed over to eradicate moa populations. The possibility of analyzing ancient DNA to identify past diseases of extinct animals is being explored. However, evidence of such diseases is difficult to determine directly from paleoecological or archaeological remains. For these reasons, it is hard to determine the likelihood that introduced disease organisms were a cause of the decline of moa, but they are potentially significant. While the last of these possible causes remains speculative, defined clues exist for the action of the first 2 causes. The story of moa species and their demise raises ecological issues on the vulnerability of species to human-caused changes, including altered vegetative cover of the landscape, change in the physical environment, and modification of the flora and fauna of a region by eliminating some species and introducing others. Po 39 Passage 3. Forest fire suppression. Forest fires have recently increased in intensity and extent in some forest types throughout the western United States. This recent increase in fires has resulted partly from climate change and partly from human activities, for complicated reasons that foresters came increasingly to understand about 30 years ago but whose relative importance is still debated. One factor is the direct effect of logging, which often turns the forest into something approximating a huge pile of kindling. The ground in a logged forest may remain covered with branches and treetops, left behind when the valuable trunks are carted away. A dense growth of new vegetation springs up, further increasing the forest's fuel loads. And the trees logged and removed are of course the biggest and most fire-resistant individuals, leaving behind smaller and more flammable trees. Another factor is that the United States Forest Service in the first decade of the 1900s adopted the policy of fire suppression for the obvious reason that it did not want valuable timber to go up in smoke, or people's homes and lives to be threatened. The Forest Service's announced goal became put out every forest fire by 10 o'clock a.m. on the morning after the day when it is first reported. Firefighters became much more successful at achieving the goal after 1945, thanks to improved firefighting technology. For a few decades the amount of land burned annually decreased by 80%. That happy situation began to change in the 1980s, due to the increasing frequency of large forest fires that were essentially impossible to extinguish unless rain and low winds combined to help. People began to realize that the United States federal government's fire suppression policy was contributing to those big fires, and that natural fires caused by lightning had previously played an important role in maintaining forest structure. The natural role of fire varies with altitude, tree species, and forest type. To make Montana's low-altitude ponderosa pine forest as an example, historical records, plus counts of annual tree rings and datable fire scars on tree stumps, demonstrated that a ponderosa pine forest experiences a lightning-lit fire about once a decade under natural conditions. The mature ponderosa trees have bark 2 inches thick and are relatively resistant to fire, which instead burns out the understory, the lower layer, of fire-sensitive Douglas fir seedlings that have grown up since the previous fire. But after only a decade's growth until the next fire, those young seedling plants are still too low for fire to spread from them into the crowns of the ponderosa pine trees. Hence the fire remains confined to ground and understory. As a result, many natural ponderosa pine forests have a park-like appearance, with low fuel loads, big trees spaced apart, and a relatively clear understory. However, loggers concentrated on removing those big, old, valuable, fire-resistant ponderosa pines, while fire suppression for decades let the understory fill up with Douglas fir saplings that would in turn become valuable when full-grown. Tree densities increased from 30 to 200 trees per acre, the forest's fuel load increased by a factor of 6, and the government repeatedly failed to appropriate money to thin out the saplings. When a fire finally does start in a sapling-choked forest, whether due to lightning or human carelessness or intentional arson, the dense, tall saplings may become a ladder that allows the fire to jump into the crowns of the trees. The outcome is sometimes an unstoppable inferno. Foresters now identify the biggest problem in managing western forests as what to do with those increased fuel loads that built up during the previous half-century of effective fire suppression. In the wetter eastern United States, dead trees rot away more quickly than in the drier west, where more dead trees persist like giant matchsticks. In an ideal world, the Forest Service would manage and restore the forests, thin them out, and remove the dense understory by cutting or by controlled small fires. But no politician or voter wants to spend what it would cost to do that. Po 40. Po 40 Passage 1. Ancient Athens. One of the most important changes in Greece during the period from 800 BC to 500 BC was the rise of the polis, or city-state, and each polis developed a system of government that was appropriate to its circumstances. The problems that were faced and solved in Athens were the sharing of political power between the established aristocracy and the emerging other classes, and the adjustment of aristocratic ways of life to the ways of life of the new polis. It was the harmonious blending of all of these elements that was to produce the classical culture of Athens. Entering the polis age, Athens had the traditional institutions of other Greek proto-democratic states, an assembly of adult males, an aristocratic council, and annually elected officials. Within this traditional framework the Athenians, between 600 BC and 450 BC, evolved what Greeks regarded as a fully fledged democratic constitution, though the right to vote was given to fewer groups of people than is seen in modern times. The first steps toward change were taken by Solon in 594 BC, when he broke the aristocracy's stranglehold on elected offices by establishing wealth rather than birth as the basis of office holding, abolishing the economic obligations of ordinary Athenians to the aristocracy, and allowing the assembly to overrule the decisions of local courts in certain cases. The strength of the Athenian aristocracy was further weakened during the rest of the century by the rise of a type of government known as a tyranny, which is a form of interim rule by a popular strongman. The Pisistratides, as the succession of tyrants were called, strengthened Athenian central administration at the expense of the aristocracy by appointing judges throughout the region, producing Athens' first national coinage, and adding and embellishing festivals that tended to focus attention on Athens rather than on local villages of the surrounding region. By the end of the century, the time was ripe for more change. The tyrants were driven out, and in 508 BC a new reformer, Cleisthenes, gave final form to the developments reducing aristocratic control already underway. Cleisthenes' principal contribution to the creation of democracy at Athens was to complete the long process of weakening family and clan structures, especially among the aristocrats, and to set in their place locality-based corporations called domes, which became the point of entry for all civic and most religious life in Athens. Out of the domes were created 10 artificial tribes of roughly equal population. From the domes, by either election or selection, came 500 members of a new council, 6,000 jurors for the courts, 10 generals, and hundreds of commissioners. The assembly was sovereign in all matters, but in practice delegated its power to subordinate bodies such as the council, which prepared the agenda for the meetings of the assembly, and courts, which took care of most judicial matters. Various committees acted as an executive branch, implementing policies of the assembly and supervising, for instance, the food and water supplies in public buildings. This wide-scale participation by the citizenry in the government distinguished the democratic form of the Athenian polis from other less liberal forms. The effect of Cleisthenes' reforms was to establish the superiority of the Athenian community as a whole over local institutions without destroying them. National politics rather than local or dem politics became the focal point. At the same time, entry into national politics began at the dem level and gave local loyalty a new focus, Athens itself. Over the next 2 centuries the implications of Cleisthenes' reforms were fully exploited. During the 5th century BC the Council of 500 was extremely influential in shaping policy. In the next century, however, it was the mature assembly that took on decision-making responsibility. By any measure other than that of the aristocrats, who had been upstaged by the supposedly inferior people, the Athenian democracy was a stunning success. Never before, or since, have so many people been involved in the serious business of self-governance. It was precisely this opportunity to participate in public life that provided a stimulus for the brilliant unfolding of classical Greek culture. Po 40 Passage 2. Latitude and biodiversity. When we look at the way in which biodiversity is distributed over the land surface of the planet, we find that it is far from even. The tropics contain many more species overall than an equivalent area at the higher latitudes. This seems to be true for many different groups of animals and plants. Why is it that higher latitudes have lower diversities than the tropics? Perhaps it is simply a matter of land area. The tropics contain a larger surface area of land than higher latitudes, a fact that is not always evident when we examine commonly used projections of Earth's curved surface, since this tends to exaggerate the areas of land in the higher latitudes, and some biogeographers regard the differences in diversity as a reflection of this effect. But an analysis of the data by biologist Klaus Rode does not support this explanation. Although area may contribute to biodiversity, it is certainly not the whole story. Otherwise, large land masses would always be richer in species. Productivity seems to be involved instead, though perhaps its influence isn't direct. Where conditions are most suitable for plant growth, that is, where temperatures are relatively high and uniform, and where there is an ample supply of water, one usually finds large masses of vegetation. This leads to a complex structure in the layers of plant material in a tropical rainforest. For example, a very large quantity of plant material builds up above the surface of the ground. There is also a large mass of material developed below ground as root tissues, but this is less apparent. Careful analysis of the above-ground material reveals that it is arranged in a series of layers, the precise number of layers varying with age and the nature of the forest. The arrangement of the biological mass of the vegetation into layered forms is termed its structure. Structure is essentially the architecture of vegetation, and as in the case of tropical forests, it can be extremely complicated. In a mature floodplain tropical forest in the Amazon River basin, the canopy takes on a stratified structure. There are 3 clear peaks in leaf cover at heights of approximately 3, 6, and 30 meters above the ground, and the very highest layer, at 50 meters, corresponds to the very tall trees that stand free of the main canopy and form an open layer of their own. So, such a forest contains essentially 4 layers of canopy. Forests in temperate lands often have just 2 canopy layers, so they have much less complex architecture. Structure has a strong influence on the animal life inhabiting a site. It forms the spatial environment within which an animal feeds, moves around, shelters, lives, and breeds. It even affects the climate on a very local level by influencing light intensity, humidity, and both the range and extremes of temperature. An area of grassland vegetation with very simple structure, for example, has a very different microclimate at the ground level from that experienced in the upper canopy. Wind speeds are lower, temperatures are lower during the day, and the relative humidity is much greater near the ground. The complexity of the microclimate is closely related to the complexity of structure and vegetation, and generally speaking, the more complex the structure of vegetation, the more species of animal are able to make a living there. The high plant biomass of the tropics leads to a greater spatial complexity in the environment, and this leads to a higher potential for diversity in the living things that can occupy a region. The climates of the higher latitudes are generally less favorable for the accumulation of large quantities of biomass. Hence, the structure of vegetation is simpler and the animal diversity is consequently lower. Po 40 Passage 3. Amphibian thermoregulation. In contrast to mammals and birds, amphibians are unable to produce thermal energy through their metabolic activity, which would allow them to regulate their body temperature independent of the surrounding or ambient temperature. However, the idea that amphibians have no control whatsoever over their body temperature has been proven false, because their body temperature does not always correspond to the surrounding temperature. While amphibians are poor thermoregulators, they do exercise control over their body temperature to a limited degree. Physiological adaptations can assist amphibians in colonizing habitats where extreme conditions prevail. The tolerance range in body temperature represents the range of temperatures within which a species can survive. One species of North American newt is still active when temperatures drop to -2 degrees Celsius, while one South American frog feels comfortable even when temperatures measure to 41 degrees Celsius, the highest body temperature measured in a free-ranging amphibian. Recently it has been shown that some North American frog and toad species can survive up to 5 days with a body temperature of -6 degrees Celsius with approximately 1/3 of their body fluids frozen. The other tissues are protected because they contain the frost protective agents glycerin or glucose. Additionally, in many species the tolerance boundaries are flexible and can change as a result of acclimatization. Frog species that remain exposed to the sun despite high diurnal temperatures exhibit some fascinating modifications in the skin structure that function as morphological adaptations. Most amphibian skin is fully water permeable and is therefore not a barrier against evaporation or solar radiation. The African savanna frog Hyperoleus viridi flavus stores guanine crystals in its skin, which enable it to better reflect solar radiation, thus providing protection against overheating. The tree frog Philomedusa salvageae responds to evaporative losses with gland secretions that provide a greasy film over its entire body that helps prevent desiccation. However, behavior is by far the most important factor in thermoregulation. The principal elements in behavioral thermoregulation are basking, heat exchange with substrates such as rock or earth, and diurnal and annual avoidance behaviors, which include moving to shelter during the day for cooling and hibernating or estivating. Heliothermy is especially common among frogs and toads. It allows them to increase their body temperature by more than 10 degrees Celsius. The Andean toad Buphospinologus exposes itself immediately after sunrise on moist ground and attains its preferred body temperature by this means, long before either ground or air is correspondingly warmed. A positive side effect of this approach is that it accelerates the digestion of the prey consumed overnight, thus also accelerating growth. Thigmothermy is a behavior present in most amphibians, although pressing against the ground serves a dual purpose: heat absorption by conductivity and water absorption through the skin. The effect of thigmothermy is especially evident in the Andean toad during rainfall. Its body temperature corresponds to the temperature of the warm earth and not to the much cooler air temperature. Avoidance behavior occurs whenever physiological and morphological adaptations are insufficient to maintain body temperature within the vital range. Nocturnal activity in amphibians with low tolerance for high ambient temperatures is a typical thermoregulatory behavior of avoidance. Seasonal avoidance behavior is extremely important in many amphibians. Species whose habitat lies in the temperate latitudes are confronted by lethal low temperatures in winter, while species dwelling in semi-arid regions are exposed to long dry, hot periods in summer. In amphibians, hibernation occurs in mud or deep holes away from frost. North of the Pyrenees Mountains, the Naturgec toad offers a good example of hibernation, passing the winter duck deep into sandy ground. Conversely, Naturgecs in southern Spain remain active during the mild winters common to the region and are instead forced into inactivity during the dry, hot summer season. Summer estivation also occurs by burrowing into the ground or hiding in cool, deep rock crevasses to avoid desiccation and lethal ambient temperature. Amphibians are therefore hardly at mercy of ambient temperature, since by means of the mechanisms described above they are more than exercise some control over their body temperature. Po41. Po41 Passage 1. Navajo Art. The Navajo, a Native American people living in the southwestern United States, live in small scattered settlements. In many respects, such as education, occupation, and leisure activities, their life is like that of other groups that contribute to the diverse social fabric of North American culture in the 21st century. At the same time, they have retained some traditional cultural practices that are associated with particular art forms. For example, the most important traditional Navajo rituals include the production of large floor paintings. These are actually made by pouring thin, finely controlled streams of colored sands or pulverized vegetable and mineral substances, pollen, and flowers in precise patterns on the ground. The largest of these paintings may be up to 5.5 meters in diameter and cover the entire floor of a room. Working from the inside of the design outward, the Navajo artist and his assistants will sift the black, white, bluish-gray, orange, and red materials through their fingers to create the finely detailed imagery. The paintings and chants used in the ceremonies are directed by well-trained artists and singers who enlist the aid of spirits who are impersonated by masked performers. The 24 known Navajo chants can be represented by up to 500 sand paintings. These complex paintings serve as memory aids to guide the singers during the performance of the ritual songs, which can last up to 9 days. The purpose and meaning of the sand paintings can be explained by examining one of the most basic ideals of Navajo society, embodied in their word hozo. It coexists with Hoxo in a world where opposing forces of dynamism and stability create constant change. When the world, which was created in beauty, becomes ugly and disorderly, the Navajo gather to perform rituals with songs and make sand paintings to restore beauty and harmony to the world. Some illness is itself regarded as a type of disharmony. Thus, the restoration of harmony through a ceremony can be part of a curing process. Men make sand paintings that are accurate copies of paintings from the past. The songs sung over the paintings are also faithful renditions of songs from the past. By recreating these arts, which reflect the original beauty of creation, the Navajo bring beauty to the present world. As relative newcomers to the Southwest, a place where their climate, neighbors, and rulers could be equally inhospitable, the Navajo created these art forms to affect the world around them, not just through the recounting of the actions symbolized, but through the beauty and harmony of the artworks themselves. The paintings generally illustrate ideas and events from the life of a mythical hero, who, after being healed by the gods, gave gifts of songs and paintings. Working from memory, the artists recreate the traditional form of the image as accurately as possible. The Navajo are also world famous for the designs on their woven blankets. Navajo women own the family flocks, control the shearing of the sheep, the carding, the spinning, and dyeing of the thread, and the weaving of the fabrics. While the men who make faithful copies of sand paintings from the past represent the principle of stability in Navajo thought, women embody dynamism and create new designs for every weaving they make. Weaving is a paradigm of the creativity of a mythic ancestor named Spider-Woman who wove the universe as a cosmic web that united earth and sky. It was she who, according to legend, taught Navajo women how to weave. As they prepare their materials and weave, Navajo women imitate the transformations that originally created the world. Working on their looms, Navajo weavers create images through which they experience harmony with nature. It is their means of creating beauty and thereby contributing to the beauty, harmony, and healing of the world. Thus, weaving is a way of seeing the world and being part of it. Po 41 Passage 2. Climate of Venus. Earth has abundant water in its oceans, but very little carbon dioxide in its relatively thin atmosphere. By contrast, Venus is very dry, and its thick atmosphere is mostly carbon dioxide. The original atmospheres of both Venus and Earth were derived at least in part from gases spewed forth, or outgassed, by volcanoes. The gases that emanate from present-day volcanoes on Earth, such as Mount St. Helens, are predominantly water vapor, carbon dioxide, and sulfur dioxide. These gases should therefore have been important parts of the original atmospheres of both Venus and Earth. Much of the water on both planets is also thought to have come from impacts from comets, icy bodies formed in the outer solar system. In fact, water probably once dominated the Venusian atmosphere. Venus and Earth are similar in size and mass, so Venusian volcanoes may well have outgassed as much water vapor as on Earth, and both planets would have had about the same number of comets strike their surfaces. Studies of how stars evolved suggest that the early Sun was only about 70% as luminous as it is now, so the temperature in Venus' early atmosphere must have been quite a bit lower. Thus water vapor would have been able to liquefy and form oceans on Venus. But if water vapor and carbon dioxide were once so common in the atmospheres of both Earth and Venus, what became of Earth's carbon dioxide? And what happened to the water on Venus? The answer to the first question is that carbon dioxide is still found in abundance on Earth, but now, instead of being in the form of atmospheric carbon dioxide, it is either dissolved in the oceans or chemically bound into carbonate rocks, such as the limestone and marble that formed in the oceans. If Earth became as hot as Venus, much of its carbon dioxide would be boiled out of the oceans and baked out of the crust. Our planet would soon develop a thick, oppressive carbon dioxide atmosphere much like that of Venus. To answer the question about Venus' lack of water, we must return to the early history of the planet. Just as on present-day Earth, the oceans of Venus limited the amount of atmospheric carbon dioxide by dissolving it in the oceans and binding it up in carbonate rocks. But being closer to the Sun than Earth is, enough of the liquid water on Venus would have vaporized to create a thick cover of water vapor clouds. Since water vapor is a greenhouse gas, this humid atmosphere, perhaps denser than Earth's present-day atmosphere, but far less dense than the atmosphere that envelops Venus today, would have efficiently trapped heat from the Sun. At first, this would have had little effect on the oceans of Venus. Although the temperature would have climbed above 100 degrees C, the boiling point of water at sea level on Earth, The added atmospheric pressure from water vapor would have kept the water in Venus' oceans in the liquid state. This hot and humid state of affairs may have persisted for several 100 million years. But as the sun's energy output slowly increased over time, the temperature at the surface would eventually have risen above 374 degrees Celsius. Above this temperature, no matter what the atmospheric pressure, Venus' oceans would have begun to evaporate, and the added water vapor in the atmosphere would have increased the greenhouse effect. This would have made the temperature even higher and caused the oceans to evaporate faster, producing more water vapor. That, in turn, would have further intensified the greenhouse effect and made the temperature climb higher still. Once Venus' oceans disappeared, so did the mechanism for removing carbon dioxide from the atmosphere. With no oceans to dissolve it, outgassed carbon dioxide began to accumulate in the atmosphere, intensifying the greenhouse effect even more. Temperatures eventually became high enough to bake out any carbon dioxide that was trapped in carbonate rocks. This liberated carbon dioxide formed the thick atmosphere of present-day Venus. Over time, the rising temperatures would have leveled off, solar ultraviolet radiation having broken down atmospheric water vapor molecules into hydrogen and oxygen. With all the water vapor gone, the greenhouse effect would no longer have accelerated. Po 41 Passage 3. Trade and early state formation. Bartering was a basic trade mechanism for many thousands of years. Often sporadic and usually based on notions of reciprocity, it involved the mutual exchange of commodities or objects between individuals or groups. Redistribution of these goods through society lay in the hands of chiefs, religious leaders, or kin groups. Such redistribution was a basic element in chiefdoms. The change from redistribution to formal trade, often based on regulated commerce that perhaps involved fixed prices and even currency, was closely tied to growing political and social complexity and hence to the development of the state in the ancient world. In the 1970s, a number of archaeologists gave trade a primary role in the rise of ancient states. British archaeologist Colin Renfrew attributed the dramatic flowering of the Minoan civilization on Crete and through the Aegean to intensified trading contacts and to the impact of olive and vine cultivation on local communities. As agricultural economies became more diversified and local food supplies could be purchased both locally and over longer distances, a far-reaching economic interdependence resulted. Eventually, this led to redistribution systems for luxuries and basic commodities, systems that were organized and controlled by Minoan rulers from their palaces. As time went on, the self-sufficiency of communities was replaced by mutual dependence. Interest in long-distance trade brought about some cultural homogeneity from trade and gift exchange, and perhaps even led to piracy. Thus, intensified trade and interaction, and the flowering of specialist crafts, in the complex process of positive feedback, led to much more complex societies based on palaces, which were the economic hubs of a new Minoan civilization. Renfrew's model made some assumptions that are now discounted. For example, he argued that the introduction of domesticated vines and olives allowed a substantial expansion of land under cultivation and helped to power the emergence of complex society. Many archaeologists and paleobotanists now question this view, pointing out that the available evidence for cultivated vines and olives suggests that they were present only in the later Bronze Age. Trade, nevertheless, was probably one of many variables that led to the emergence of palace economies in Minoan Crete. American archaeologist William Rathge developed a hypothesis that considered an explosion in long-distance exchange a fundamental cause of Mayan civilization in Mesoamerica. He suggested that the lowland Mayan environment was deficient in many vital resources, among them obsidian, salt, stone for grinding maize, and many luxury materials. All these could be obtained from the nearby highlands, from the Valley of Mexico, and from other regions, if the necessary trading networks came into being. Such connections, and the trading expeditions to maintain them, could not be organized by individual villages. The Maya lived in a relatively uniform environment, where every community suffered from the same resource deficiencies. Thus, argued Rathge, long-distance trade networks were organized through local ceremonial centers and their leaders. In time, this organization became a state, and knowledge of its functioning was exportable, as were pottery, tropical bird feathers, specialized stone materials, and other local commodities. Rathge's hypothesis probably explains part of the complex process of Mayan state formation, but it suffers from the objection that suitable alternative raw materials can be found in the lowlands. It could be, too, that warfare became a competitive response to population growth and to the increasing scarcity of prime agricultural land, and that it played an important role in the emergence of the Mayan states. Now that we know much more about ancient exchange and commerce, we know that, because no one aspect of trade was an overriding cause of cultural change or evolution in commercial practices, trade can never be looked on as a unifying factor or as a primary agent of ancient civilization. Many ever-changing variables affected ancient trade, among them the demand for goods. There were also the logistics of transportation, the extent of the trading network, and the social and political environment. Intricate market networks channeled supplies along well-defined routes. Authorities at both ends might regulate the profits fed back to the source, providing the incentive for further transactions. There may or may not have been a market organization. Extensive long-distance trade was a consequence rather than a cause of complex societies. Po 42. Po 42 Passage 1. Geographic isolation of species. Biologist Ernst Mayr defined a species as an actually or potentially interbreeding population that does not interbreed with other such populations when there is opportunity to do so. A key event in the origin of many species is the separation of a population with its gene pool from other populations of the same species, thereby preventing population interbreeding. With its gene pool isolated, a separate population can follow its own evolutionary course. In the formation of many species, the initial isolation of a population seems to have been a geographic barrier. This mode of evolving new species is called allopatric speciation. Many factors can isolate a population geographically. A mountain range may emerge and gradually split a population of organisms that can inhabit only lowland lakes. Certain fish populations might become isolated in this way. Similarly, a creeping glacier may gradually divide a population, or a land bridge such as the Isthmus of Panama may form and separate the marine life from the ocean waters on either side. How formidable must a geographic barrier be to keep populations apart? It depends on the ability of the organisms to move across barriers. Birds and coyotes can easily cross mountains and rivers. The passage of wind-blown tree pollen is also not hindered by such barriers, and the seeds of many plants may be carried back and forth on animals. In contrast, small rodents may find a deep canyon or a wide river an effective barrier. For example, the Grand Canyon, in the southwestern United States, separate the range of the white-tailed antelope squirrel from that of the closely related Harris antelope squirrel. Smaller, with a shorter tail that is white underneath, the white-tailed antelope squirrel inhabits deserts north of the canyon and west of the Colorado River in Southern California. Harris antelope squirrel has a more limited range in deserts south of the Grand Canyon. Geographic isolation creates opportunities for new species to develop, but it does not necessarily lead to new species because speciation occurs only when the gene pool undergoes enough changes to establish reproductive barriers between the isolated population and its parent population. The likelihood of allopatric speciation increases when a population is small as well as isolated, making it more likely than a large population to have its gene pool changed substantially. For example, in less than 2 million years, small populations of stray animals and plants from the South American mainland that managed to colonize the Galapagos Islands gave rise to all the species that now inhabit the islands. When oceanic islands are far enough apart to permit populations to evolve in isolation, but close enough to allow occasional dispersions to occur, they are effectively outdoor laboratories of evolution. The Galapagos Island chain is one of the world's greatest showcases of evolution. Each island was born from underwater volcanoes and was gradually covered by organisms derived from strays that rode the ocean currents and winds from other islands and continents. Organisms can also be carried to islands by other organisms, such as seabirds that travel long distances with seeds clinging to their feathers. The species on the Galapagos Islands today, most of which occur nowhere else, descended from organisms that floated, flew, or were blown over the sea from the South American mainland. For instance, the Galapagos Island chain has a total of 13 species of closely related birds called Galapagos Finches. These birds have many similarities but differ in their feeding habits and their beak type, which is correlated with what they eat. Accumulated evidence indicates that all 13 finch species evolved from a single small population of ancestral birds that colonized one of the islands. Completely isolated on the island after migrating from the mainland, the founder population may have undergone significant changes in its gene pool and become a new species. Later, a few individuals of this new species may have been blown by storms to a neighboring island. Isolated on this second island, the second founder population could have evolved into a second new species, which could later recolonize the island from which its founding population emigrated. Today each Galapagos island has multiple species of finches, with as many as 10 on some islands. Po 42 Passage 2. Explaining dinosaur extinction. Dinosaurs rapidly became extinct about 65 million years ago as part of a mass extinction known as the KT event, because it is associated with a geological signature known as the KT boundary, usually a thin band of sedimentation found in various parts of the world. Many explanations have been proposed for why dinosaurs became extinct. For example, some have blamed dinosaur extinction on the development of flowering plants, which were supposedly more difficult to digest and could have caused constipation or indigestion, except that flowering plants first evolved in the early Cretaceous, about 60 million years before the dinosaurs died out. In fact, several scientists have suggested that the duck-billed dinosaurs and horned dinosaurs, with their complex battery of grinding teeth, evolved to exploit this new resource of rapidly growing flowering plants. Others have blamed extinction on competition from the mammals, which allegedly ate all the dinosaur eggs, except that mammals and dinosaurs appeared at the same time in the late Triassic, about 190 million years ago, and there is no reason to believe that mammals suddenly acquired a taste for dinosaur eggs after 120 million years of coexistence. Some explanations fail because there is no way to scientifically test them, and they cannot move beyond the realm of speculation and guesswork. This focus on explaining dinosaur extinction misses an important point. The extinction at the end of the Cretaceous was a global event that killed off organisms up and down the food chain. It wiped out many kinds of plankton in the ocean and many marine organisms that lived on the plankton at the base of the food chain. These included a variety of clams and snails, and especially the ammonites, a group of shell squid-like creatures that dominated the Mesozoic seas and had survived many previous mass extinctions. The KT event marked the end of the marine reptiles, such as the mosasaurs and the plesiosaurs, which were the largest creatures that had ever lived in the seas and which ruled the seas long before whales evolved. On land, there was also a crisis among the land plants, in addition to the disappearance of dinosaurs. So any event that can explain the destruction of the base of the food chain can better explain what happened to organisms at the top of the food chain, such as the dinosaurs. By contrast, any explanation that focuses strictly on the dinosaurs completely misses the point. The Cretaceous extinctions were a global phenomenon, and dinosaurs were just a part of a bigger picture. According to one theory, the age of dinosaurs ended suddenly 65 million years ago when a giant rock from space plummeted to Earth. Estimated to be 10 to 15 kilometers in diameter, this bolide was traveling at cosmic speeds of 20-70 kilometers per second, or 45,000-156,000 miles per hour. Such a huge mass traveling at such tremendous speeds carries an enormous amount of energy. When the bullet struck, this energy was released and generated a huge shock wave that leveled everything for thousands of kilometers around the impact and caused most of the landscape to burst into flames. The bullet struck an area of the Yucatan Peninsula of Mexico known as Chicxulub, excavating a crater 15-20 kilometers deep and at least 170 kilometers in diameter. The impact displaced huge volumes of seawater, causing much flood damage in the Caribbean. Meanwhile, the bullet itself excavated 100 cubic kilometers of rock and debris from the site, which rose to an altitude of 100 kilometers. Most of it fell back immediately, but some of it remained as dust in the atmosphere for months. This material, along with the smoke from the fires, shrouded Earth, creating a form of nuclear winter. According to computerized climate models, global temperatures fell to near the freezing point, photosynthesis halted, and most plants on land and in the sea died. With the bottom of the food chain destroyed, dinosaurs could not survive. Po 42 Passage 3. Callisto and Ganymede. From 1996 to 1999, the Galileo spacecraft passed through the Jovian system, providing much information about Jupiter's satellites. Callisto, the outermost of Jupiter's 4 largest satellites, orbits the planet in 17 days at a distance from Jupiter of 2 million kilometers. Like our own moon, Callisto rotates in the same period as it revolves, so it always keeps the same face toward Jupiter. Its noontime surface temperature is only about -140 degrees Celsius, so water ice is stable on its surface year-round. Callisto has a diameter of 4.820 kilometers, almost the same as that of Mercury. Its mass is only 1/3 as great, which means its density must be only 1/3 as great as well. This tells us that Callisto has far less of the rocky metallic materials found in the inner planets and must instead be an icy body through much of its interior. Callisto is not fully differentiated, meaning separated into layers of different density materials. Astronomers can tell that it lacks a dense core from the details of its gravitational pull on the Galileo spacecraft during several very close flybys. This fact surprised scientists, who expected that all the big icy moons would be differentiated. It is much easier for an icy body to differentiate than for a rocky one, since the melting temperature of ice is so low. Only a little heating will soften the ice and get the process started, allowing the rock and metal to sink to the center and the slushy ice to flow to the surface. Yet Callisto seems to have frozen solid before the process of differentiation was complete. Like our moon's islands, the surface of Callisto is covered with impact craters. The survival of these craters tells us that an icy object can form and retain impact craters in its surface. In thinking of ice so far from the Sun, it is important not to judge its behavior from that of the much warmer ice we know on Earth. At the temperatures of the outer solar system, ice on the surface is nearly as hard as rock, and behaves similarly. Ice on Callisto does not deform or flow like ice in glaciers on Earth. Callisto is unique among the planet-sized objects of the solar system in its absence of interior forces to drive geological evolution. The satellite was born dead and has remained geologically dead for more than 4 billion years. Ganymede, another of Jupiter's satellites and the largest in our solar system, is also cratered, but less so than Callisto. About 1/4 of its surface seems to be as old and heavily cratered. The rest formed more recently, as we can tell by the sparse covering of impact craters as well as the relative freshness of the craters. Ganymede is a differentiated world, like the terrestrial planets. Measurements of its gravity field tell us that the rock and metal sank to form a core about the size of our moon, with a mantle and crust of ice floating above it. In addition, the Galileo spacecraft discovered that Ganymede has a magnetic field, the signature of a partially molten interior. Ganymede is not a dead world, but rather a place of continuing geological activity powered by an internal heat source. Much of its surface may be as young as 500 million years. The younger terrain is the result of tectonic and volcanic forces. Some features formed when the crust cracked, flooding many of the craters with water from the interior. Extensive mountain ranges were formed from compression of the crust, forming long ridges with parallel valleys spaced 1 to 2 kilometers apart. In some places older impact craters were split and pulled apart. There are even indications of large-scale crustal movements that are similar to the plate tectonics of Earth. Why is Ganymede different from Callisto? Possibly the small difference in size and internal heating between the two led to this divergence in their evolution. But more likely the gravity of Jupiter is to blame for Ganymede's continuing geological activity. Ganymede is close enough to Jupiter that tidal forces from the giant planet may have episodically heated its interior and triggered major convulsions on its crust. Po 43. Po 43 Passage 1. The Empire of Alexander the Great. In 334 BC, Alexander the Great took his Greek armies to the east and in only a few years completed his creation of an empire out of much of Southwest Asia. In the new empire, barriers to trade and the movement of peoples were removed. Markets were put in touch with one another. In the next generation, thousands of Greek traders and artisans would enter this wider world to seek their fortunes. Alexander's actions had several important consequences for the region occupied by the empire. The first of these was the expansion of Greek civilization throughout the Middle East. Greek became the great international language. Towns and cities were established not only as garrisons but as centers for the diffusion of Greek language, literature, and thought, particularly through libraries, as at Antioch and the most famous of all, at Alexandria in Egypt, which would be the finest in the world for the next 1,000 years. Second, this internationalism spelled the end of the classical Greek city-state, the unit of government in ancient Greece, and everything it stood for. Most city-states had been quite small in terms of citizenry, and this was considered to be a good thing. The focus of life was the agora, the open marketplace where assemblies could be held and where issues of the day, as well as more fundamental topics such as the purpose of government or the relationship between law and freedom, could be discussed and decisions made by individuals in person. The philosopher Plato felt that the ideal city-state should have about 5,000 citizens. Because to the Greeks it was important that everyone in the community should know each other. In decision-making, the whole body of citizens together would have the necessary knowledge and order generally to reach the right decision, even though the individual might not be particularly qualified to decide. The philosopher Aristotle, who lived at a time when the city-state system was declining, believed that a political entity of 100,000 simply would not be able to govern itself. This implied that the city-state was based on the idea that citizens were not specialists but had multiple interests and talents, each a so-called jack-of-all-trades who could engage in many areas of life and politics. It implied a respect for the wholeness of life and a consequent dislike of specialization. It implied economic and military self-sufficiency. But with the development of trade and commerce in Alexander's empire came the growth of cities. It was no longer possible to be a jack-of-all-trades. One now had to specialize, and with specialization came professionalism. There were getting to be too many persons to know. An easily observable community of interests was being replaced by a multiplicity of interests. The city-state was simply too small time. Third, Greek philosophy was opened up to the philosophy and religion of the East. At the peak of the Greek city-state, religion played an important part. Its gods, such as Zeus, father of the gods, and his wife Hera, were thought of very much as being like human beings but with superhuman abilities. Their worship was linked to the rituals connected with one's progress through life, birth, marriage, and death, and with invoking protection against danger, making prophecies, and promoting healing, rather than to any code of behavior. Nor was there much of a theory of afterlife. Even before Alexander's time, a life spent in the service of their city-state no longer seemed ideal to Greeks. The Athenian philosopher Socrates was the first person in Greece to propose a morality based on individual conscience rather than the demands of the state, and for this he was accused of not believing in the city's gods and so corrupting the youth, and he was condemned to death. Greek philosophy, or even a focus on conscience, might complement religion but was no substitute for it, and this made Greeks receptive to the religious systems of the Middle East, even if they never adopted them completely. The combination of the religious instinct of Asia with the philosophic spirit of Greece spread across the world in the era after Alexander's death, blending the culture of the Middle East with the culture of Greece. Po 43 Passage 2. The origin of petroleum. Petroleum is defined as a gaseous, liquid, and semi-solid naturally occurring substance that consists chiefly of hydrocarbons. Petroleum is therefore a term that includes both oil and natural gas. Petroleum is nearly always found in marine sedimentary rocks. In the ocean, microscopic phytoplankton and bacteria are the principal sources of organic matter that is trapped and buried in sediment. Most of the organic matter is buried in clay that is slowly converted to a fine-grained sedimentary rock known as shale. During this conversion, organic compounds are transformed to oil and natural gas. Sampling on the continental shelves and along the base of the continental slopes has shown that fine muds beneath the seafloor contain up to 8% organic matter. Two additional kinds of evidence support the hypothesis that petroleum is a product of the decomposition of organic matter. Oil possesses optical properties known only in hydrocarbons derived from organic matter, and oil contains nitrogen and certain compounds believed to originate only in living matter. A complex sequence of chemical reactions is involved in converting the original solid organic matter to oil and gas, and additional chemical changes may occur in the oil and gas even after they have formed. It is now well established that petroleum migrates through aquifers and can become trapped in reservoirs. Petroleum migration is analogous to groundwater migration. When oil and gas are squeezed out of the shale in which they originated and enter a body of sandstone or limestone somewhere above, they migrate readily because sandstones and limestones are much more permeable than any shale. The force of molecular attraction between oil and quartz or carbonate minerals is weaker than that between water and quartz or carbonate minerals. Hence, because oil and water do not mix, water remains fastened to the quartz or carbonate grains, while oil occupies the central parts of the larger openings in the porous sandstone or limestone. Because oil is lighter than water, it tends to glide upward past the carbonate and quartz-held water. In this way, oil becomes segregated from the water. When it encounters a trap, it can form a pool. Most of the petroleum that forms in sediments does not find a suitable trap and eventually makes its way, along with groundwater, to the surface of the sea. It is estimated that no more than 0.1% of all the organic matter originally buried in a sediment is eventually trapped in an oil pool. It is not surprising, therefore, that the highest ratio of oil and gas pools to volume of sediment is found in rock no older than 2.5 million years, young enough so that little of the petroleum has leaked away, and that nearly 60% of all oil and gas discovered so far has been found in strata that formed in the last 65 million years. This does not mean that older rocks produced less petroleum. It simply means that oil in older rocks has had a longer time in which to leak away. How much oil is there in the world? This is an extremely controversial question. Many billions of barrels of oil have already been pumped out of the ground. A lot of additional oil has been located by drilling but is still waiting to be pumped out. Possibly a great deal more oil remains to be found by drilling. Unlike coal, the volume of which can be accurately estimated, the volume of undiscovered oil can only be guessed at. Guesses involve the use of accumulated experience from a century of drilling. Knowing how much oil has been found in an intensively drilled area, such as eastern Texas, experts make estimates of probable volumes in other regions where rock types and structures are similar to those in eastern Texas. Using this approach and considering all the sedimentary basins of the world, experts estimate that somewhere between 1,500 and 3,000 billion barrels of oil will eventually be discovered. Po 43 Passage 3. El Nino. The cold Humboldt Current of the Pacific Ocean flows toward the equator along the coasts of Ecuador and Peru in South America. When the current approaches the equator, the westward flowing trade winds cause nutrient-rich cold water along the coast to rise from deeper depths to more shallow ones. This upwelling of water has economic repercussions. Fishing, especially for anchovies, is a major local industry. Every year during the months of December and January, a weak, warm countercurrent replaces the normally cold coastal waters. Without the upwelling of nutrients from below to feed the fish, fishing comes to a standstill. Fishers in this region have known the phenomenon for hundreds of years. In fact, this is the time of year they traditionally set aside to tend to their equipment and await the return of cold water. The residents of the region have given this phenomenon the name of El Nino, which is Spanish for the child, because it occurs at about the time of the celebration of birth of the Christ child. While the warm water countercurrent usually lasts for 2 months or less, there are occasions when the disruption to the normal flow lasts for many months. In these situations, water temperatures are raised not just along the coast, but for thousands of kilometers offshore. Over the last few decades, the term El Niño has come to be used to describe these exceptionally strong episodes and not the annual event. During the past 60 years, at least 10 El Niños have been observed. Not only do El Niños affect the temperature of the equatorial Pacific, but the strongest of them impact global weather. The processes that interact to produce an El Niño involve conditions all across the Pacific, not just in the waters off South America. Over 60 years ago, Sir Gilbert Walker, a British scientist, discovered a connection between surface pressure readings at weather stations on the eastern and western sides of the Pacific. He noted that a rise in atmospheric pressure in the eastern Pacific is usually accompanied by a fall in pressure in the western Pacific and vice versa. He called this seesaw pattern the Southern Oscillation. It was later realized that there is a close link between El Niño and the Southern Oscillation. In fact, the link between the two is so great that they are often referred to jointly as ENSO. During a typical year, the eastern Pacific has a higher pressure than the western Pacific does. This east-to-west pressure gradient enhances the trade winds over the equatorial waters. This results in a warm surface current that moves east to west at the equator. The western Pacific develops a thick, warm layer of water, while the eastern Pacific has the cold Humboldt current enhanced by upwelling. However, in other years the Southern Oscillation, for unknown reasons, swings in the opposite direction, dramatically changing usual conditions described above, with pressure increasing in the western Pacific and decreasing in the eastern Pacific. This change in the pressure gradient causes the trade winds to weaken or, in some cases, to reverse. This then causes the warm water in the western Pacific to flow eastward, increasing sea surface temperatures in the central and eastern Pacific. The eastward shift signals the beginning of an El Niño. Scientists try to document as many past El Niño events as possible by piecing together bits of historical evidence, Circassian surface temperature records, daily observations of atmospheric pressure and rainfall, fisheries records from South America, and the writings of Spanish colonists dating back to the 15th century. From such historical evidence we know that El Niños have occurred as far back as records go. It would seem that they are becoming more frequent. Records indicate that during the 16th century, an El Niño occurred on average every 6 years. Evidence gathered over the past few decades indicates that El Niños are now occurring on average a little over every 2 years. Even more alarming is the fact that they appear to be getting stronger. The 1997 to 1998 El Niño brought copious and damaging rainfall to the southern United States, from California to Florida. Snowstorms in the northeast portion of the United States were more frequent and intense than in most years. Po 44. Po 44 Passage 1. From fish to terrestrial vertebrates. One of the most significant evolutionary events that occurred on Earth was the transition of water-dwelling fish to terrestrial tetrapods. Fish probably originated in the oceans, and our first records of them are in marine rocks. However, by the Devonian period, they had radiated into almost all available aquatic habitats, including freshwater settings. One of the groups whose fossils are especially common in rocks deposited in freshwater is the Lobe Finfish. The freshwater Devonian Lobe Finfish Ripidistion crossopterygian is of particular interest to biologists studying tetrapod evolution. These fish lived in river channels and lakes on large deltas. The delta rocks in which these fossils are found are commonly red due to oxidized iron minerals, indicating that the deltas formed in a climate that had alternate wet and dry periods. If there were periods of drought, any adaptations allowing the fish to survive the dry conditions would have been advantageous. In these repedistions, several such adaptations existed. It is known that they had lungs as well as gills for breathing. Cross-sections cut through some of the fossils reveal that the mud filling the interior of the carcass differed in consistency and texture depending on its location inside the fish. These differences suggest a sac-like cavity below the front end of the gut that can only be interpreted as a lung. Gills were undoubtedly the main source of oxygen for these fish, but the lungs served as an auxiliary breathing device for gulping air when the water became oxygen depleted, such as during extended periods of drought. So, these fish had already evolved one of the prime requisites for living on land, the ability to use air as a source of oxygen. A second adaptation of these fish was in the structure of the lobe fins. The fins were thick, fleshy, and quite sturdy, with a median axis of bone down the center. They could have been used as feeble locomotor devices on land, perhaps good enough to allow a fish to flop its way from one pool of water that was almost dry to an adjacent pond that had enough water and oxygen for survival. These fins eventually changed into short, stubby legs. The bones of the fins of a Devonian repedistion exactly match in number and position the limb bones of the earliest known tetrapods, the amphibians. It should be emphasized that the evolution of lungs and limbs was in no sense an anticipation of future life on land. These adaptations developed because they helped fish to survive in their existing aquatic environment. What ecological pressures might have caused fishes to gradually abandon their watery habitat and become increasingly land-dwelling creatures? Changes in climate during the Devonian may have had something to do with this if freshwater areas became progressively more restricted. Another impetus may have been new sources of food. The edges of ponds and streams surely had scattered dead fish and other water-dwelling. In addition, plants had emerged into terrestrial habitats in areas near streams and ponds, and crabs and other arthropods were also members of this earliest terrestrial community. Thus, by the Devonian, the land habitat marginal to fresh water was probably a rich source of protein that could be exploited by an animal that could easily climb out of water. Evidence from teeth suggests that these earliest tetrapods did not utilize land plants as food. They were presumably carnivorous and had not developed the ability to feed on plants. How did the first tetrapods make the transition to a terrestrial habitat? Like early land plants such as rhinophytes, they made only a partial transition. They were still quite tied to water. However, many problems that faced early land plants were not applicable to the first tetrapods. The ancestors of these animals already had a circulation system, and they were mobile, so that they could move to water to drink. Furthermore, they already had lungs, which repedistions presumably used for auxiliary breathing. The principal changes for the earliest tetrapods were in the skeletal system, changes in the bones of the fins, the vertebral column, pelvic girdle, and pectoral girdle. Po 44 Passage 2. The use of the camera obscura. The precursor of the modern camera, the camera obscura is a darkened enclosure into which light is admitted through a lens in a small hole. The image of the illuminated area outside the enclosure is thrown upside down as if by magic onto a surface in the darkened enclosure. This technique was known as long ago as the 5th century BC in China. Aristotle also experimented with it in the 4th century BC, and Leonardo da Vinci described it in his notebooks in 1490. In 1558 Giovanni Battista della Porta wrote in his 20-volume work Major Naturalis instructions for adding a convex lens to improve the quality of the image thrown against a canvas or panel in the darkened area where its outlines could be traced. Later, portable camera obscuras were developed, with interior mirrors and drawing tables on which the artist could trace the image. For the artist, this technique allows forms in linear perspective to be drawn precisely as they would be seen from a single viewpoint. Mirrors were also used to reverse the projected images to their original positions. Did some of the great masters of painting, then, trace their images using a camera obscura. Some art historians are now looking for clues of artists' use of such devices. One of the artists whose paintings are being analyzed from this point of view is the great Dutch master, Jan Vermeer, who lived from 1632 to 1675 during the flowering of art and science in the Netherlands, including the science of optics. Vermeer produced only about 30 known paintings, including his famous The Art of Painting. The room shown in it closely resembles the room in other Vermeer paintings, with lighting coming from a window on the left, the same roof beams, and similar floor tiles, suggesting that the room was fitted with a camera obscura on the side in the foreground. The map hung on the opposite wall was a real map in Vermeer's possession, reproduced in such faithful detail that some kind of tracery is suspected. When one of Vermeer's paintings was X-rayed, it did not have any preliminary sketches on the canvas beneath the paint, but rather the complete image drawn in black and white without any trial sketches. Vermeer did not have any students, did not keep any records, and did not encourage anyone to visit his studio, facts that can be interpreted as protecting his secret use of a camera obscura. In recent times, the British artist David Hockney has published his investigations into the secret use of the camera obscura, claiming that for up to 400 years, many of Western art's great masters probably used the device to produce almost photographically realistic details in their paintings. He includes in this group Caravaggio, Hans Holbein, Leonardo da Vinci, Diego Velázquez, Jean-Auguste Dominique Ingres, Agnolo Bronzino, and Jan van Eyck. From an artist's point of view, Hockney observed that a camera obscura compresses the complicated forms of a three-dimensional scene into two-dimensional shapes that can easily be traced, and also increases the contrast between light and dark, leading to the chiaroscuro effect seen in many of these paintings. In Jan van Eyck's The Marriage of Giovanni Arnolfini and Giovanna Senemi, the complicated foreshortening in the chandelier and the intricate detail in the bride's garments are among the clues that Hockney thinks point to the use of the camera obscura. So what are we to conclude? If these artists did use a camera obscura, does they diminish their stature? Hockney argues that the camera obscura does not replace artistic skill in drawing and painting. In experimenting with it, he found that it is actually quite difficult to use for drawing, and he speculates that the artists probably combined their observations from life with tracing of shapes. Po 44 Passage 3. Seagrasses. Many areas of the shallow sea bottom are covered with a lush growth of aquatic flowering plants adapted to live submerged in seawater. These plants are collectively called seagrasses. Seagrass beds are strongly influenced by several physical factors. The most significant is water motion, currents and waves. Since seagrass systems exist in both sheltered and relatively open areas, they are subject to differing amounts of water motion. For any given seagrass system, however, the water motion is relatively constant. Seagrass meadows in relatively turbulent waters tend to form a mosaic of individual mounds, whereas meadows in relatively calm waters tend to form flat, extensive carpets. The seagrass beds, in turn, dampen wave action, particularly if the blades reach the water surface. This damping effect can be significant to the point where just 1 meter into a seagrass bed the wave motion can be reduced to zero. Currents are also slowed as they move into the bed. The slowing of wave action and currents means that seagrass beds tend to accumulate sediment. However, this is not universal and depends on the currents under which the bed exists. Seagrass beds under the influence of strong currents tend to have many of the lighter particles, including seagrass debris, moved out, whereas beds in weak current areas accumulate lighter detrital material. It is interesting that temperate seagrass beds accumulate sediments from sources outside the beds, whereas tropical seagrass beds derive most of their sediments from within. Since most seagrass systems are depositional environments, they eventually accumulate organic material that leads to the creation of fine-grained sediments with a much higher organic content than that of the surrounding unvegetated areas. This accumulation, in turn, reduces the water movement and the oxygen supply. The high rate of metabolism of the microorganisms in the sediments causes sediments to be anaerobic. Below the first few millimeters, according to ecologist J. W. Kenworthy, Anaerobic processes of the microorganisms in the sediment are an important mechanism for regenerating and recycling nutrients and carbon, ensuring the high rates of productivity, that is, the amount of organic material produced that are measured in those beds. In contrast to other productivity in the ocean, which is confined to various species of algae and bacteria dependent on nutrient concentrations in the water column, seagrasses are rooted plants that absorb nutrients from the sediment or substrate. They are, therefore, capable of recycling nutrients into the ecosystem that would otherwise be trapped in the bottom and rendered unavailable. Other physical factors that have an effect on seagrass beds include light, temperature, and desiccation. For example, water depth and turbidity together or separately control the amount of light available to the plants and the depth to which the seagrasses may extend. Although marine botanist W. A. Setchell suggested early on that temperature was critical to the growth and reproduction of eelgrass, it has since been shown that this particularly widespread seagrass grows and reproduces at temperatures between 2 and 4 degrees Celsius in the Arctic and at temperatures up to 28 degrees Celsius on the northeastern coast of the United States. Still, extreme temperatures, in combination with other factors, may have dramatic detrimental effects. For example, in areas of the cold North Atlantic, ice may form in winter. Researchers Robertson and Mann note that when the ice begins to break up, the wind and tides may move the ice around, scouring the bottom and uprooting the eelgrass. In contrast, at the southern end of the eelgrass range, on the southeastern coast of the United States, temperatures over 30 degrees Celsius in summer cause excessive mortality. Seagrass beds also decline if they are subjected to too much exposure to the air. The effect of desiccation is often difficult to separate from the effect of temperature. Most seagrass beds seem tolerant of considerable changes in salinity and can be found in brackish waters as well as in full-strength seawater. Po 45. Po 45 Passage 1. Microscopes the Beringia landscape. During the peak of the last ice age, Northeast Asia and Alaska were connected by a broad land mass called the Bering Land Bridge. This land bridge existed because so much of Earth's water was frozen in the great ice sheets that sea levels were over 100 meters lower than they are today. Between 25,000 and 10,000 years ago, Siberia, the Bering Land Bridge, and Alaska shared many environmental characteristics. These included a common mammalian fauna of large mammals, a common flora composed of broad grasslands as well as windswept dunes and tundra, and a common climate with cold, dry winters and somewhat warmer summers. The recognition that many aspects of the modern flora and fauna were present on both sides of the Bering Sea as remnants of the Ice Age landscape led to this region being named Beringia. It is through Beringia that small groups of large mammal hunters, slowly expanding their hunting territories, eventually colonized North and South America. On this archaeologists generally agree, but that is where the agreement stops. One broad area of disagreement in explaining the peopling of the Americas is the domain of paleoecologists, but it is critical to understanding human history. What was Beringia like? The Beringian landscape was very different from what it is today. Broad, windswept valleys, glaciated mountains, sparse vegetation, and less moisture created a rather forbidding landmass. This landmass supported herds of now extinct species of mammoth, bison, and horse, and somewhat modern versions of caribou, muskox, elk, and saiga antelope. These grazers supported in turn a number of impressive carnivores, including the giant short-faced bear, the saber-toothed cat, and a large species of lion. The presence of mammal species that require grassland vegetation has led Arctic biologist Dale Guthrie to argue that while cold and dry, there must have been broad areas of dense vegetation to support herds of mammoth, horse, and bison. Further, nearly all of the Ice Age fauna had teeth that indicate an adaptation to grasses and sedges. They could not have been supported by a modern flora of mosses and lichens. Guthrie has also demonstrated that the landscape must have been subject to intense and continuous winds, especially in winter. He makes this argument based on the anatomy of horse and bison, which do not have the ability to search for food through deep snow cover. They need landscapes with strong winds that remove the winter snows, exposing the dry grasses beneath. Guthrie applied the term mammoth steppe to characterize this landscape. In contrast, Paul Colinvaux has offered a counter-argument based on the analysis of pollen in lake sediments dating to the last ice age. He found that the amount of pollen recovered in these sediments is so low that the Beringian landscape during the peak of the last glaciation was more likely to have been what he termed a polar desert, with little or only sparse vegetation. In no way was it possible that this region could have supported large herds of mammals and thus, human hunters. Guthrie has argued against this view by pointing out that radiocarbon analysis of mammoth, horse, and bison bones from Beringian deposits revealed that the bones date to the period of most intense glaciation. The argument seemed to be at a standstill until a number of recent studies resulted in a spectacular suite of new finds. The first was the discovery of a 1,000 square kilometer preserved patch of Beringian vegetation dating to just over 17,000 years ago, the peak of the last ice age. The plants were preserved under a thick ash fall from a volcanic eruption. Investigations of the plants found grasses, sedges, mosses, and many other varieties and a nearly continuous cover, as was predicted by Guthrie. But this vegetation had a thin root mat with no soil formation, demonstrating that there was little long-term stability in plant cover, a finding supporting some of the arguments of Colinvaux. A mixture of continuous but thin vegetation supporting herds of large mammals is one that seems plausible and realistic with the available data. Po 45 Passage 2. Wind pollination. Pollen, a powdery substance, which is produced by flowering plants and contains male reproductive cells, is usually carried from plant to plant by insects or birds, but some plants rely on the wind to carry their pollen. Wind pollination is often seen as being primitive and wasteful in costly pollen, and yet it is surprisingly common, especially in higher latitudes. Wind is very good at moving pollen a long way. Pollen can be blown for hundreds of kilometers, and only birds can get pollen anywhere near as far. The drawback is that wind is obviously unspecific as to where it takes the pollen. It is like trying to get a letter to a friend at the other end of the village by climbing onto the roof and throwing an armful of letters into the air and hoping that one will end up in the friend's garden. For the relatively few dominant tree species that make up temperate forests, where there are many individuals of the same species within pollen range, this is quite a safe gamble. If a number of people in the village were throwing letters off roofs, your friend would be bound to get one. By contrast, in the tropics, where each tree species has few, widely scattered individuals, the chance of wind blowing pollen to another individual is sufficiently slim that animals are a safer bet as transporters of pollen. Even tall trees in the tropics are usually not wind-pollinated despite being in windy conditions. In a similar way, trees in temperate forests that are insect-pollinated tend to grow as solitary, widely spread individuals. Since wind-pollinated flowers have no need to attract insects or other animals, they have dispensed with bright petals, nectar, and scent. These are at best a waste and at worst an impediment to the transfer of pollen in the air. The result is insignificant-looking flowers and catkins. Wind pollination does, of course, require a lot of pollen. Birch and hazel trees can produce 5.5 and 4 million grains per catkin, respectively. There are various adaptations to help as much of the pollen go as far as possible. Most deciduous wind-pollinated trees produce their pollen in the spring while the branches are bare of leaves to reduce the surrounding surfaces that compete with the stigmas. For pollen, evergreen conifers, which do not shed their leaves, have less to gain from spring flowering, and, indeed, some flower in the autumn or winter. Pollen produced higher in the top branches is likely to go farther. It is windier and the pollen can be blown farther before hitting the ground. Moreover, dangling catkins like hazel hold the pollen in until the wind is strong enough to bend them, ensuring that pollen is only shed into the air when the wind is blowing hard. Weather is also important. Pollen is shed primarily when the air is dry to prevent too much sticking to wet surfaces or being knocked out of the air by rain. Despite these adaptations, much of the pollen fails to leave the top branches, and only between 0.5% and 40% gets more than 100 meters away from the parent. But once this far, significant quantities can go a kilometer or more. Indeed, pollen can travel many thousands of kilometers at high altitudes. Since all this pollen is floating around in the air, it is no wonder that when pollinated trees are a major source of allergies. Once the pollen has been snatched by the wind, the fate of the pollen is obviously up to the vagaries of the wind, but not everything is left to chance. Windborne pollen is dry, rounded, smooth, and generally smaller than that of insect-pollinated plants. But size is a two-edged sword. Small grains may be blown farther, but they are also more prone to be whisked past the waiting stigma, because smaller particles tend to stay trapped in the fast-moving